Yeah, so we'll start recording it at this point. Okay. All right. Yeah, so for the domain of this function, it's going to be all real numbers except 2 and minus 2. So I could write it as the interval from minus infinity up to minus 2, but not including minus 2. And then I would need everything from minus 2 up to 2, and then everything from 2 out to infinity, okay? So that would be like one way that you could write out the domain using interval notation. And yeah, here would be a good place where you could use the union symbol as someone talked about before. All right. Let's talk about the horizontal asymptotes next. Okay, so to find the horizontal asymptote, so there were 3 possibilities. Yeah, you want to look at the degree of the numerator and the denominator. In this case, both numerator and denominator have the same degree of 2. And so when they have the same degree, you want to take the ratio of the leading coefficients to get your horizontal asymptote, okay? So in the numerator, yeah, the leading coefficient of the numerator was 3, because that's the coefficient of your x squared term. The leading coefficient of your denominator is -1, because that's the coefficient of x squared down here, okay? So you take the ratio, so 3 over -1. So y equals -3 is going to be the equation of your horizontal asymptote, okay? All right. And so you do this whenever the degree of the numerator and the denominator are equal, okay? Okay. Yeah, when we're looking at the vertical asymptotes and the wholes, that's where you'll want to focus on the numerator as well as the denominator. But for the domain, you only focus on the denominator. So even if there's a cancellation where the denominator was 0, that will still be a place where your function was undefined. So therefore, for the purpose of the domain, you only look at where the denominator is 0. And it doesn't matter whether you can cancel it out or not. Okay. Now for rational functions, you'll only have one horizontal asymptote. But other types of functions can definitely have more than one horizontal asymptote though, okay? And I'd probably see some examples of that as you go along. Right, and then the y equals -3 was just coming from taking the ratio of the leading coefficients. So because the numerator and denominator had the same degree of 2, we took their coefficients, which were the 3 and the -1. So 3 over -1 gave us y equals -3 as the equation of our horizontal asymptote, okay? And then, yeah, when we look at the vertical and the vertical asymptotes holes, okay? Now let's take our function and let's also work on factoring the numerator as well. LC, that was me rereading, but it stands for leading coefficient. All right.
I have a question.
Yeah, go for it.
Yes, I understand that when x equal 2 and x equal -2 is when the function is undefined. So we have to put that two holes in there. And when
Right.
y is equal -3, what happened to the function? It's not a hole, is it?
Yeah, it's a horizontal asymptote is what it is.
Yeah, what is mean by horizontal asymptote? Is that mean that's when the
Oh,
function change directions?
no, I see what you're saying. Yeah. A horizontal asymptote at y equals -3. That means your function will be doing something like this. So here I'm going to draw the line y equals -3. So it would be maybe somewhere down here. And then this function, let's see here. Okay. This function, I think, is going to do something like this. Oh, that was -20. Okay. So at some point, your function, I think, is going to be like, its graph will do something like this, where it's just going to get like closer and closer to this line y equals -3, but it's never like actually going to like cross it. It just like keeps getting closer and closer like this. Whenever your graph is doing something like that, you have a horizontal asymptote at that location. Okay. It's like graphically, this is what's going on at y equals -3. It's a horizontal asymptote, which means that the graph is doing something like this. Okay. Does that answer the question?
Yeah, I guess so.
Okay. All right. And we are talk more about horizontal and vertical asymptotes on day 3, which is the first day of calculus content. So asymptotes are kind of hard to talk about without any mention of calculus. Rational functions are simple enough where we can actually find their asymptotes without using any calculus. But in day 3, we'll talk more about horizontal and vertical asymptotes, and maybe it'll make more sense when we do that on day 3. Okay. Okay. And yeah, going back real quick, the 2 and the -2. So when you're looking for the domain, you just want to find where the denominator is equal to 0. So that's what I did up here. So where the denominator is equal to 0, those are the places that you need to remove from the number line to get your domain. Okay. All right. Any other questions at the moment? Okay. All right. Now for the vertical asymptotes and the holes. So this is where we also want to pay attention to the numerator. So we already found the denominator before. It was 2 minus x and 2 plus x. If we want to factor the numerator, in this situation, the leading coefficient is not equal to 1. But notice in this example that we can actually factor a 3 out from every term first. And then after we factor the 3 out from every term, we do get a quadratic with a leading coefficient of 1. Okay. So that makes it easier to factor if you factor out the 3 first. Okay. So who wants to tell me how to factor the numerator now? Yeah, very good. So yeah, x minus 2, x plus 1, okay? And then the point of factoring numerator and denominator is for vertical asymptotes and wholes, you want to see if you can cancel anything out, okay? So here, this is maybe a little bit tricky, but in the numerator, we have an x minus 2, and in the denominator, we have a 2 minus x. So we can sort of cancel those out, but I want to maybe like add an extra step to see like what happens when you cancel them out. So x minus 2 and 2 minus x, how are those two expressions related to each other? Inverses, yeah, that's kind of the idea. So yeah, by inverses, I think what you mean is one of them is the negative of the other, right? Okay. So if you take 2 minus x and if you just multiply it by -1, you see that this will give you minus 2 plus x. So it is the same as x minus 2, okay? So that means in the numerator, I can take the x minus 2 and replace x minus 2 with -2 minus x. Okay. And once I pull a minus sign out from the x minus 2, that leaves us with a 2 minus x in both the numerator and the denominator. So then you can actually cancel those out. So altogether, after factoring numerator and denominator, and then doing any cancellations that you can, we're left with this expression here, okay? So now the vertical asymptote, you're gonna look at the expression after you make any cancellations. So from here, look at where the denominator is equal to 0. So in this case, the denominator is 0 at x equals -2. So x equals -2 is going to give us a vertical asymptote, okay? So for this function, what's going to be happening is at x equals -2, which let's say is maybe located here in the graph. What's going to be happening? -2, that's positive. So I think the graph will do something like this. Okay. So at x equals -2, your function again does something where it like gets really close to that line but never crosses it. And in this case, it just kind of like goes like down and up forever as it gets closer and closer to -2, but it never actually crosses it or touches it. Okay. That's kind of what a vertical asymptote will look like graphically. Okay. Now, if you look at what we had before you made any cancellation, so over here, so we know that at x equals -2, the denominator was equal to 0. But x equals +2, that was another place where the denominator was 0. Okay. Okay. So yeah, -2 was a vertical asymptote. So what about x equals 2, which is the value that sort of got canceled out here? Whoops. If you're able to make a cancellation like this, then you don't get a vertical asymptote. So instead, you're going to get a hole at any location that you were able to cancel out, okay? Okay. And then I guess like graphically what the hole looks like is well, it just means the graph will do something like this where it has a hole at that one value. That's what's going on. Okay. Okay, so that was kind of an example of a rational function, finding the domain, horizontal and vertical asymptotes, and then finding any holes in them. Okay. I have some other examples. I guess this one's not super complicated. Okay, let's look at this one as well. So we're going to do the same thing, find the domain, and then horizontal vertical asymptotes, and then any holes that I may have. So let's talk about the domain of this function first. Okay. So we want to do the same thing that we did in the previous example. So let's try to find where the denominator is equal to 0. Yeah, that's actually a good question. So how do we know, like when you have a vertical asymptote, whether it's like going down or up like this? Or if you have a horizontal asymptote, how do you know if it's approaching from above, like this picture, or maybe it was approaching from below like that? Okay. That's where you maybe need to do a little bit more analysis. But yeah, what I would recommend is plugging in some points to get a sense for what's going on. So in this picture here, plug in a number to the left of -2. And if you get like negative 1,000, right? That tells you that the graph is going to be doing something like this. It's going to be going down. And like here, you can plug in a number to the right of +2. And then when you do that, you'll probably get a large positive number. And that kind of tells you that the graph was trending upwards. Okay. Okay, great. So I tried to do that mentally in my head real quick for this example when I was drawing these pictures. But I might have made a mistake, so I might have gotten the picture wrong because I was just trying to do it in my head. Okay. Okay. Yeah, in this case, so again, to find a domain, typical, start by looking at where the denominator is 0. For this function here, at what locations is the denominator equal to 0? Yeah, okay. So this equation has no real solutions. So this means that the denominator is never going to be equal to 0. And because the denominator is never 0, that means the domain will be all real numbers. So it's going to be just minus infinity to infinity. Now, as for how to tell that there are no real solutions, one thing you can actually do is like actually try to solve for x. So if I were to -3 to both sides, so I try to move it over. And then like here, if you want to solve for x, you'd want to try to square root this, right? And here, once you get to this point, you kind of see what the issue is. Yeah, so you're trying to square root a negative number, and at least in a calculus class, you don't really consider that, okay? All right, good. All right. What about the horizontal asymptote? Okay, so for rational functions, remember that you can find the horizontal asymptotes by looking at the degree of the numerator and denominator. Yeah, so here the denominator has a higher degree. Okay. So if the denominator has a large degree, then that means that y equals 0 will be your horizontal asymptote, okay? Yeah, and in your calculus 1 and 2 classes, you don't really consider imaginary numbers. So if you had a situation like this in a problem in your calculus course, you would just say there were no real solutions and just move on from there, okay? If you are an electrical engineer, you will be doing stuff with imaginary numbers later on in some of your more advanced classes. If you're a physics or math major, I guess you would also do some stuff with imaginary numbers as well in some of your higher level classes. Yeah. Okay. And then I guess what about the vertical asymptotes and the holes for this example? Okay, so remember that vertical asymptotes or holes, right? They would be located where your denominator is 0. But here we already saw that the denominator will never actually equal 0. So this is an example where we have a rational function that has no vertical asymptotes and also no holes in the graph. Okay? So not every rational function is going to have an asymptote or a hole. Okay. Okay, great. And yeah, I guess let's do this. I think this was the last example that I had for rational functions. All right, so let's just kind of finish this one off, okay? So who can tell me what the domain of this function will be? Or what should we do to find a domain? Yeah, good. Set the denominator equal to 0. And then to solve for x here, you can either factor it or I guess I'll do what someone else suggested in the previous example. You can just move 1 to the other side. The only thing you want to be careful about is when you try the square root to solve for x, just remember that there's 2 possible solutions, which is the plus and the minus square root, okay? So sometimes I guess like a mistake that I've seen somewhat often from students is if they try to solve an equation like this, they might forget to put the plus or minus in front of the square root. And if you were to actually factor this equation instead of doing this approach, if you factor it, it's more obvious that +1 and -1 are both solutions. But if you don't factor it, just keep in mind that whenever you have like x squared equal to something and you're solving for x, you have to do plus or minus the square root to make sure that you're accounting for both possibilities. Okay? So that's maybe a reason why I do sort of prefer to factor, just because I've seen students mess this up before and only get one of the solutions. Yeah, difference of squares works. It would have given you the x minus 1, x plus 1 factorization. Okay, but so then we found the two places where the denominator is 0. So then this function is defined at every other value of x. So for the domain, you want to include everything except for -1 and +1, okay? So in the interval notation, it will look something like that. All right, good. And then what about the horizontal asymptotes? Okay, yeah, so looking at the degree of the numerator and the denominator, yeah, notice that the numerator has the larger degree this time. Because here the degree of the numerator is 3 because of the x cubed term, whereas the degree of the denominator is 2 because of the x squared. So when the numerator has a large degree, that means you have no horizontal asymptotes, okay? Okay, good. And then I guess lastly, for the vertical asymptotes and holes, okay? Let's take the function and now let's also factor the numerator as well as the denominator. Okay. So I guess we already talked about the denominator. It factored as x minus 1, x plus 1. And the numerator, you want to start by factoring the x squared out first. And if you factor out the x squared, you're going to get 1 minus x remaining, okay? And then this is similar to what we saw before where we have 1 minus x in the numerator, we have x minus 1 in the denominator. So you can almost cancel them out, but in order to like do a cancellation, you can factor a minus sign out from one of those two expressions. So for example, in the 1 minus x term, if you pull a minus sign, well, I guess it doesn't matter, but x minus 1, if you were to pull a minus sign out from it, you will get minus 1 minus x. So again, these are just like negatives of each other. So let's say in the denominator, you can take that x minus 1 and replace it with a minus 1 minus x. And then from there, make your cancellation. Okay. Now, once you've done this, so you're not always going to be able to factor some or cancel something out, but if you are able to make any cancellations, then look at the final results to get your vertical asymptote. So in this example, we get 1 vertical asymptote when x plus 1 is equal to 0, so when x is negative 1. But to find your holes, you want to look at what got canceled out. So what got canceled out was actually the 1 minus x. So if you set that equal to 0 to solve for x, we get x equals 1 as the location of the hole, okay? All right, any questions about this? All right. So I guess I have just a little bit more prepared for today. So we started with polynomial functions. We moved on to the rational functions. So I'm just going to end the day by talking about algebraic functions. Yeah, so it's certainly possible that there's no whole. So if you were not able to cancel anything out from the numerator and denominator, then you would not have any wholes. Okay. As for what you mean by a different type of discontinuity, I guess we'll talk more continuity and discontinuity. We get to day 3 and day 4 because that's actually a calculus concept. What other type of discontinuity? Yeah, so you mean like a jump discontinuity, I guess, or something like that. We'll talk more about those when we get to, I guess, day 3. We'll talk about those. Okay. Okay. But yeah, so let's end the day talking about the algebraic functions. So rational functions, they only involve integer powers of x. It's like a whole numbers, like x squared, x cubed, for instance. So algebraic functions can also involve square roots and cube roots and other like fourth root, etc. Okay. And so I guess I want to first kind of recall some properties of exponents. Okay. So I guess first thing is remember that square root of x is equivalent to x to a power of 1/2. Okay. So in a sense, you can say that algebraic functions allow for powers of x that are not whole numbers. So like here we have like a fraction exponent rather than like a whole number as an exponent. Okay. And then remember that like a cube root would be x to the power of 1/3. Fourth root would be x to a power of 1/4, and so forth. So in general, the nth root of a number x, it's equivalent to writing x to a power of 1/n. Okay. All right, and then some of the other properties of exponents that I just wanted to mention over here. So when you're multiplying powers of x, or more generally, two expressions with the same base but different powers like this, the rule is to add the exponents together. So for example, like x squared times x cubed will give you x to the power of 5 because you add 2 plus 3. And so when would you multiply the 2 and the 3? And that's when you have a situation like this where you have x to a power, but then that's all raised to another power. This is the situation where you would multiply the exponents rather than add them. So here you'll get x to a power of 6. Okay. So sometimes I see students getting these mixed up, and they'll add the exponents when they should have multiplied them, or they'll multiply them when they should have added them. Okay. These are some other properties. So when you have a product all raised to a power, you can distribute that exponent to each factor. Okay. So it works for products and also works for fractions or quotients as well. Okay. And then just a reminder on how negative exponents work. So when you have x to a power of negative n, remember that a negative in the exponent just moves it to the denominator. So x to the minus n is actually just 1 over x to the n. So it doesn't become negative or anything like that. It just moves to the denominator. And then I feel like this doesn't happen too often, but if you did have a negative exponent in the denominator, then you can actually move it up into the numerator with a positive exponent. So 1 over x to the minus 2, and that's just the same as x squared. And you can easily like justify that because we know that x to the minus 2 is 1 over x squared, according to this rule up here. And then when you're dividing by a fraction, you would and multiply by the reciprocal. So 1 over x to the minus 2 is equivalent to x squared. Okay. All right. And I just wanted to maybe make sure that we're kind of comfortable with working with fractional powers of something. So here I've got 9 to a power of 3/2. Who can tell me without using a calculator what 9 to the 3/2 is equal to? Six. Not quite. So 9, how did you get 6? Okay, let's ignore that. So yeah, 27 is the correct answer. So let's understand how we got this, okay? So I guess for 9 to the 3/2, there's kind of two ways you can think about it. So I'll kind of illustrate both approaches. So you should think of 9 to the 3/2 as 9 to the power of 3 and then to the power of 1/2, okay? So that's kind of utilizing this rule up here, because 3 times 1/2 is 3/2. That's what I was kind of thinking, yeah. So if you did 9 times 2 over 3, that's how you would have gotten 6 as your answer. Okay. Okay, but the other way you can think about 9 to the 3/2 though is 9 to the power of 1/2 and then taking that and cubing it. Okay. And between these two approaches, I think the second one is simpler because 9 to the 3/2 is just taking the square root of 9, and then we'll try to cube that. We know square root of 9 is 3, so this is 3 cubed. So if you just multiply 3 times, you get the answer of 27, okay? Now, yeah, let me see the, oh, yeah, that's, OneNote does weird things like this. So, so I have a separate laptop pulled up so I can see what's going on in e-learning as I'm working in OneNote. And what I notice is that when I'm trying to point at something, it doesn't seem to share what I'm pointing at unless I do this, and then you can actually see where my mouse is. But sometimes when I do that, OneNote leaves an extra dash that doesn't go away. So that's what that was, okay? Okay. And then if we had something like square root of 27, so 27 doesn't have a nice square root, but it is possible to kind of simplify this. So if you think of 27 as being 9 times 3, you can apply this property up here and apply the square root to the 9 and the 3 separately. Okay. So the idea of this is square root is the same as raising to a power of 1/2. So according to this property up here that I mentioned, you can distribute the 1/2 to each factor. And that's what justifies being able to apply the square root to the 9 and the 3 individually, okay? And then square root of 9 is 3. So ultimately, you can simplify this as 3 times the square root of 3, okay? Now, I will say that in your calculus class, your professor is not going to care if you leave it as square root of 27. So you would not actually be required to simplify as 3 times square root of 3. But maybe in a problem, it might work out more cleanly if you do make the simplification. So although you may not be required to do this, but perhaps in a problem, it actually works out nicer if you do simplify it this way, okay? Oh, that's right. I wanted to show you guys this as well. So 1 over root 2, okay? So many of you were taught that, my colleague shaking his head here. So many of you were taught to, I think you call this rationalizing it, I think is what it was called, but you were taught to multiply numerator and denominator by square root of 2. So that in the denominator, square root of 2 times square root of 2 is 2. So you get rid of the square root when you do this, right? And probably many of you were taught that you can't leave a square root in the denominator. So you have to do this rationalizing process to get rid of the square root, okay? So I just wanted to make sure that all of you knew that in your calculus course, your professors do not care if there is a square root in the denominator. So if you have 1 over root 2, you can just leave it as 1 over root 2. You really don't need to exactly rationalize it the way that I did here. There's nothing wrong if you do rationalize it, but sometimes it makes me smile when I see students do this like automatically. It's like, no, you actually don't have to do this, okay? Sort of, yeah, okay. All right. So it makes your life maybe a little bit easier to know that you don't have to do this now. What else do I have planned? Oh, okay, yeah. Just a pretty simple-ish example. Let's say you had this equation and oh, actually, this is something interesting. Okay, yeah, good. Let's solve for x in this equation, okay? So does anyone have any suggestions as to what I should do first if I want to solve for x? Yeah, so again, maybe try to factor out the greatest common factor. So here, the greatest common factor would be x to a power of 1/2, okay? Very good. So what would I have in the parentheses when I factor out x to the 1/2? Yeah, x squared minus 4x minus 21. So if you weren't too sure how to do that, basically when you pull out the x to the 1/2, you want to minus 1/2 from all the other exponents to see what's left in the parentheses. So yeah, 5/2 minus 1/2 gives you 4 over 2. So you're left with a power of 2 at the end and so forth, okay? All right, great. From here, we can factor the quadratic. So that's going to be x minus 7 and x plus 3 equals 0. So yeah, let's set each factor equal to 0. And you get 3 solutions at first: x equals 0, x equals 7, and x equals -3. Okay, now one of these solutions is not actually a solution. So who can tell me which of these solutions actually doesn't work as a solution? And maybe you can also explain why it's not an actual solution. Okay, let me answer that question, but okay, good. So I'll come back to your question about why we subtracted the exponent. But yeah, so first, x equals -3. This is the bad solution, so you want to get rid of it, okay? And your actual solution is only going to be x equals 0 and x equals 7. So yeah, go ahead and ask your question or make your comment.
When you say x equals -3, it's not really a solution. It's called an extraneous solution.
Right. Yeah, so it's an extraneous solution because if you try to, and this is one of those cases where if you try to plug it back into the original equation to try and see if it made sense or not, right? If you try to plug back into the equation, in your equation, you've got x to the power of like 1/2 everywhere, right? So if you try to plug -3 in for x and then you try to raise it to a power of 1/2, remember this is like square rooting a negative number, which at least in your Calculus 1 and Calculus 2 courses, we don't consider this as a possibility. So that's why x equals -3 does not work as a solution, okay? 0 and 7 will work though, because if you try to plug them into your equation, you don't have any issue with square rooting a negative number. So 0 and 7 will be fine. Okay, now I guess I'll end today just by addressing the other question, which is why was I subtracting 1/2 from all the powers? So that's really coming from, I think maybe a good way to think about it is using this property up here, that when I'm multiplying like powers of x, I want to just add the exponents together. So a good way to think about it is maybe actually working backwards. If you were to, distribute the 1/2 back to the parentheses, you'd have to add 1/2 to all powers of x. And then adding the 1/2 would have given you this up here, okay? And I don't think there's really that much time left for anything else. I know there's this one quick thing that I had planned as well, so I'll just, oh yeah, okay, so let me do this real quick, and then I will post the notes in the chat if you guys want to access it, okay? But just real quick, if you guys will humor me, I have, square root of x squared here. How would you guys simplify square root of x squared? So I see a lot of wrong answers being posted in the chat right now. So yeah, okay, so this is something that seems to come up. It's going to come up in your calculus courses. It's not like a huge thing, but it is going to come up. So I want to just try to address it right now as well. Yeah, square root of x squared does not simplify as just x. Really what it simplifies as is the absolute value of x, okay? So absolute value of x is going to be equal to x, but only if x is greater than or equal to 0. If x is a negative number, though, then absolute value x would not be equal to x because x is negative, but absolute value of x is positive, right? So in this case, absolute value of x would be equal to negative x. So what's happening here is x is a negative number. So if you put a minus in front of it, it becomes positive. Okay. As for why square root of x squared is equal to absolute value of x, I think maybe just thinking of an example will clarify. So, if I ask everyone what is the square root of 4, what would you guys tell me the square root of 4 is? Yeah, square root of 4 would be equal to 2, okay? In order to get negative 2 as an answer, you have to put a negative in front of the square root to get negative 2, okay? Which is why, like, whenever you're like solving an equation like x squared equals 4, if you want to get both solutions, you have to specify both the positive and the negative of 2 in this case, okay? So really, when we talk about the square root of something, we're always, or at least mathematicians have defined the square root function to only give the positive root as the output. So if you want to specify the negative output, you need to put a negative sign in front of the square root, okay? So that means when you have something like square root of negative 2 squared, the answer is not going to be negative 2, because this is just square root of 4. So really the answer was 2, which you could think of as like the absolute value of negative 2. And that's kind of the idea of square root of x squared should be equal to the absolute value of x, not just x, okay? So that's not like a super important thing, but something that will come up in your Calculus 1 course. So I just want to try to address it here, okay? Yeah, so tomorrow my colleague Les will be leading the math workshop, and he'll be talking about exponential functions and logarithms, and also trig functions as well. So all the like really good stuff. Okay. Let me give you guys access to my notes here real quick. So give me like 1 minute. So I'll share it as a PDF. Okay. I guess maybe this is the easiest way to do it. Let's make sure that it actually worked. Okay, so I just uploaded the PDF of my notes as a file in eLearning. So there is a button that you can click near the top right. It's the second icon from the right. So if you click on that button, it'll allow you to download the file. Okay. All right, cool. Wednesday's session will be recorded as well, yes. We'll be sure that we remember to record.